Hello, and welcome to the fourth video for the computer graphics course. This video is going to go over what you need to know in WebGL to render the triangle. Before we dive into things, go over to the line where you initialized WebGL in the last project. In order to use all of the newest features that I'm going to go over in this video, go ahead and change WebGL to WebGL2. Here's what we're going to do. First, we're going to create a JavaScript array of floating point numbers to act as our triangle vertices. Second, we're going to put this data into a buffer on the GPU. Real quick, I did say in an earlier video to think of buffers as sort of like images, but in this case, just think of it as a fixed slot of memory on the GPU. This is how you might have thought of buffers before I made things more complicated in that video. Anyways, third, we're going to make a second JavaScript array and a second WebGL buffer, which will contain the indices used to draw the triangle. That step will make a lot more sense when we get to it, so don't worry if it doesn't make sense now. Next, we're going to make a couple of very small programs that will run on the GPU called shaders. These will tell the GPU what to do with the vertices we're passing it and how to actually color our triangle. We're going to link those shaders together and compile them into a program the GPU can use. We're going to connect our raw vertex data buffer to that compiled shader program with things called vertex shader attributes. Next, we'll set the viewport width and height, which you can sort of think of as setting the dimensions of our digital camera window. And finally, we'll call a draw command. Let's start with this JavaScript vertex array. Even though we know our vertices are grouped by three numbers, x, y, and z, that's something that WebGL is going to figure out later on as we tweak this further. The WebGL buffer is just going to store these vertex components one after the other contiguously in memory, like this. So let's say we have this triangle with vertices v0, v1, and v2. We know that each of these vertices will have an x, y, and a z component. So we'll represent this as v0x, v0y, and v0z, and likewise for the other three vertices. Thus, our JavaScript array will look like this. Real quick, and this really should get more attention, but it will in later videos, as this video is already going to be very daunting. These coordinates need to range from -1 to 1 here. I will explain this later in the shader section. The order does actually matter here. This is referred to as the winding order. As you can see, the points on this triangle, when read sequentially from 0 to 2, move counterclockwise on the triangle. Which of these points corresponds to V0 does not matter, so long as the other points relative to it are in counterclockwise order. This becomes especially obvious because you could always just rotate the triangle itself instead of directly changing the V0 location. The reason the order matters here is because of an optimization called backface culling. Look at this object. Objects made out of triangles don't really have anything going on internally. We're just defining the surface of objects. But we don't care about the backsides of these faces, we're not going to see them. I mentioned in one of the earlier videos that our GPU will do something called a depth test to determine which triangle is closest to the camera for each pixel, and that's the triangle that we end up rendering. This takes a bit of computation, and since we want things running as quickly as possible, we want to rule out triangles for consideration for this depth test as early as possible so that we don't waste our time. Look at this example. Imagine that this eye icon is our perspective, and we're looking at this square. We're never going to see the sides of this square, right? Since we know we shouldn't even consider the triangles that make up those sides, we'd rather not do the depth test on them if it can be helped. Well, look at this cube in Blender. More specifically, look at the triangle I've highlighted. I've now added some labels here in this video editing software, so you can imagine that the triangle indices would go something like this. You can see that these indices go in counterclockwise order. Now, I'm going to move the camera so that you can't see that face. Obviously, there's no reason to render that triangle, and, like I said before, we'd like to exclude this triangle from the depth test because it's expensive. I'll go ahead and enable wireframe mode in Blender now so that we can see through this mesh. We typically do wireframe rendering in things like computer graphics for debugging purposes, which allows us to see the backsides of triangles when we normally wouldn't be able to. Now we can see that selected triangle again. And I'm going to put those same labels for the indices back where they were before. You can see that these indices now go in clockwise order rather than counterclockwise order from where we're looking. This is how rendering algorithms are able to determine which triangles in the scene are backface triangles, so we can discard them early on instead of performing the depth test on them. All this is to say that when you're creating the order for your triangle vertex indices, make sure they're in counterclockwise order so that WebGL won't think of it as a backface and skip rendering it. Now, an additional complication I'm going to add to this project is something called indexed drawing. You can pass these vertices directly to the GPU and essentially say, okay, draw this triangle using these vertices in exactly the order I'm giving them to you in the array. Again, the order being what WebGL will use to determine that this triangle is a front-facing triangle and should be rendered. And this would honestly be the simplest thing to do in this project. But that's only because we're rendering a single triangle. And all other projects going forward are going to use a lot more than one triangle. So let's look at this quad, for example. We know our objects will be made out of triangles, so this square can be made of 2 triangles since it has these 4 unique corner vertices. Well, one way we could render this is to just treat these triangles almost like they know nothing about each other. We could list our first triangle's components as V0, V1, V2. Then we list the second triangle's components in the same list as V2, V1, and V3. Because each vertex has 3 spatial components, X, Y, and Z, our raw JavaScript array would end up looking something like this. Now, this feels sort of sloppy since we're redefining vertices V1 and V2, which are shared between the 2 triangles. What we'd like to be able to do here is just define the 4 vertices that make up the square one time, and then create another lightweight buffer, which we'll initially define as a JavaScript array, just like we did with the vertices, which will just contain the vertices for these triangles. In this square example, the array would look like 0, 1, 2, 2, 1, 3. So we're basically saying here, draw V0, V1, and V2 as a triangle, and then draw V2, V1, and V3 as a triangle. We're not having to redefine the vertices, we're just giving the indices. And of course, with these indices, we still have to make sure that we are going in counterclockwise order. Now, this whole indexed drawing operation is way overkill for the square example. We're not going to notice a performance difference. Our GPUs could certainly handle the redundant 2 vertices in our vertex array. But when we get to rendering more complicated objects, then this redundant data becomes a lot less trivial. Now let's bring things back to the code. So you'll define your triangle vertices in a JavaScript array like this, and your index array like this, making sure that the winding order is counterclockwise. Now, how do we actually get this data to the GPU? First, you're going to need to create a buffer for each array using gl.createBuffer, which will return a buffer object. Again, the buffer object is sort of like if we had just called malloc, but for the GPU. It essentially returns an address to the portion of memory you asked for. Although, unlike malloc, we don't specify the size of memory we want. It's done dynamically. Now, remember that I said WebGL is a state machine. WebGL has a set-aside funnel, or connection point, meant for bringing CPU data over to the GPU, which is exactly what we're doing. We want to connect the buffer that we created with gl.createBuffer to this connection point. We're going to use gl.bindBuffer to do this. Here, we're telling WebGL specifically which buffer on the GPU the connection point is going to be funneling data into. Importantly, there are actually a few different connection points on the GPU for different kinds of data. For example, our vertices and indices use different connection points. So, to set our buffer up to receive vertex data from JavaScript, the command will look like this: gl.bindBuffer, with the first parameter being the name of the connection point, gl.arrayBuffer, and the second argument is the buffer we're connecting it to. The reason it's called array buffer and not something more specific like vertex buffer is just historical. When they were doing all of this, they wanted the buffers to be more generic than just spatial data. But vertex data is pretty much the only thing we use this buffer for in computer graphics. The funnel does not change, only what block of memory it's bound to. It probably seems odd that we need to bind this buffer manually to this connection point, and it's definitely confusing. The reason we do this manually is because if we didn't, then we'd end up with a lot of redundancy. So WebGL and OpenGL, it just lets us do this ourselves instead of trying to do it for us because it knows that we could do it faster. For example, let's say that I wanted to render a particle system. This usually requires passing a bunch of positions corresponding to each particle over to the GPU each frame, because the positions of those particles change each frame, along with corresponding vectors for each particle which represent the velocity. If we let WebGL handle all of this binding for us, it would look like this: bind the buffer which holds the particle data, pass the particle position data over to it, and then unbind that buffer from the connection point. Then rebind the same buffer to the connection point, pass the particle velocity data over, and unbind the buffer again. Obviously, you can see the redundancy here, and binding these buffers is not a trivial action on the GPU. It takes some time. In fact, it's one of the most expensive things that we regularly do. This is the reason that we have manual control over binding buffers to the connection points between the CPU and the GPU. So instead, the particle operation can look like this: bind the buffer which holds the particle data, pass the particle position data over to it, pass the particle velocity data over to it, and then unbind the buffer. As you can see, this removes a lot of redundancy. Okay, reeling back a bit, I know this is a lot. You're going to create your JavaScript vertex and index arrays. Then you're going to be calling gl.createBuffer to grab a GPU memory handle for your vertices. And in case you're thinking it now, you'll do the exact same thing to get a handle for the index buffer. You can do that now if you'd like, but it doesn't matter. We'll go over it in a bit in the video. Next, you're going to set up the connection point from the CPU over to this buffer on the GPU with gl.bindBuffer, with the arguments gl.arrayBuffer and the buffer variables you created with gl.createBuffer. Now that our buffer is bound to the array buffer, we're finally going to pass the vertex data to the GPU with a function called gl.bufferData. The first argument to this function is the target, just like the first argument to gl.bindBuffer. As a reminder, that's gl.arrayBuffer. Sometimes people also call this the binding point. With this, we're telling WebGL to pour the data straight down that array buffer vertex funnel into the buffer we've bound there with gl.bindBuffer. The second argument is the data we're passing. You do need to wrap this into a float32 array object, since JavaScript is using 64-bit data and our GPU expects 32-bit data. This may seem odd to use less precision, but the thing is that computer graphics don't really benefit from these ultra-precise floating point numbers. We can't notice the difference. Lastly, you're going to pass in an enum that tells our GPU how we're going to be using that data. Since we're only uploading this triangle data once and won't be updating it, we'd like our GPU drivers to put this data into a part of VRAM that's optimized for reading, not writing. To do this, we pass the gl.staticDrawEnum. If this vertex data were constantly changing, like in the case of a fluid or a cloth simulation, we'd instead pass something like gl.dynamicDraw, in which case the driver would put this data into a part of VRAM more optimized for writing. Now, You can pretty much duplicate all of this for the index buffer. So you've created your index buffer with gl.createBuffer, just like you did for the vertex buffer. Now, instead of binding that buffer to gl.arrayBuffer, you're going to bind it to gl.elementArrayBuffer, which is the buffer specifically meant to handle these indices instead of vertices. Then you'll call gl.bufferData again, this time using gl.elementArrayBuffer again. Since these indices obviously aren't floats, instead of passing them as a float 32 array, you'll pass them as a 16-bit unsigned integer array. If you're unfamiliar with unsigned integers, it just means integers that can only be positive. Since we're dealing with array indices, we obviously don't want negative numbers. Lastly, since we're only uploading this data once, you'll use gl.staticDraw again. Okay, now that that nightmare's over, let's go over a topic that's actually fun, which is shaders. We will end up going over shaders in quite a lot of detail in this class, but since these videos are already overwhelming, we'll cover just what you need to know, and we'll learn more about them as needed. Shaders are small programs that run directly on the GPU. Each shader is technically made up of multiple shaders, which is slightly confusing terminology. But when I say shaders, I mostly mean the shaders that make up the shader program. For this program, and all programs in this class, the shader programs will consist of two shaders, the vertex shader and the fragment shader. Vertex shaders take as an input vertex information, like the positions of our vertices that we defined in our JavaScript array and later put into the GPU buffer. That being said, this isn't the only data we can pass here. Any data that's relevant to each vertex could be passed here, like color. The vertex shader typically applies transformations to the vertices to help us render them. This won't make much sense now, but it will in the future projects. For this project, the vertex shader won't really do anything with the vertex data, as in the vertex positions that are passed in. This is because this project is really simple and we're just rendering a triangle. For this reason, the vertex shader we'll be using for this project is just called a pass-through shader. It just takes the vertices and passes them straight through to the next step, which the GPU actually handles for us. What the GPU will do with these vertices it receives as output from the vertex shader, which is typically transformed, is perform rasterization. What this means is that it will essentially receive the data for the three transformed vertices, let's say position data and color data, and now you can imagine that it overlays a grid over this triangle so that the triangle is made up of a bunch of discrete squares. For now, just focus on the color. Imagine that the top vertex has the color blue, the bottom left vertex had the color red, and the bottom right vertex had the color green. The GPU will perform interpolation and rasterization to get all the colors in between these points in this triangle in discrete steps. I'll explain what each of these terms means now. Interpolation is easiest to first understand if we look at the edges of the triangle instead of the center area. Look at this line from the red to the blue vertex. The fragments, or little squares, over here start off pretty much fully red. The fragment on the very corner of the red vertex is, in fact, just completely red. But as it goes along the line, it's losing a bit of its red color and having blue color added, becoming purple, until it's eventually completely blue once it reaches this vertex. This fragment over here is completely devoid of any red since it's on the edge opposite the red vertex. And then everything in the center of this triangle is a mixture of the three colors. The blending action is called interpolation, and it's a pretty universal operation in mathematics. Interpolation is just one of the things that happens during rasterization. The other step is splitting this interpolated result into discrete fragments. And rasterization is a unique concept to computer graphics. This rasterization process is one of the things our GPU is extremely efficient at, and it's done for us. What makes the GPU so powerful is that it can do all of this in parallel at an enormous scale. When the vertices reach the vertex shader, they're handled completely independently of one another. And all of these fragments created in the rasterization step are handed to the fragment shader completely independent of one another as well, meaning they can all be handled in parallel. This is a huge optimization, but it can also make things more difficult because none of these components know about one another. This is one of the benefits that ray tracing has on the CPU over rasterization on the GPU. Remember, we won't just be dealing with colors in this class, but colors are easy to visualize, so I used it in this example. For this project, we're going to be passing position data through the vertex shader, so our GPUs will actually be rasterizing the positional data of the vertices, meaning that it'll get a ton of discrete positions inside the triangle that'll be passed to the fragment shader. This ability of the GPU to handle so much data in parallel is why they're ruining the world right now. Now, I'll talk about what the fragment shader does. The fragment shader is going to receive all of this interpolated and discretized data and decide how it wants that fragment to be colored in the final image based on this data. For this triangle program, the shader can be as simple as just saying, I want the fragment to be red, or whatever color you want, and that's it. Let's get into some annoying specifics for these shaders. In WebGL, the language for shaders is called GLSL, which stands for OpenGL Shading Language. So yeah, OpenGL uses the same language, and actually, so does Vulkan. It's not a hard language to use. It's similar to C syntax-wise, but I'd argue that it's usually a lot simpler than C. Real quick, in JavaScript, it'll end up taking these programs as strings. In the assignment page, I'll show you how you can keep these shaders as separate files and still easily read them in as JavaScript strings. Anyways, the first thing you have to do with this is specify the version number at the top of the file. For us, it's version 300 ES. This is the newest embedded systems version of GLSL, which is the newest version of GLSL WebGL can use. We use embedded systems versions because we have to be able to run these browsers on our phones. Next, we're going to specify the vertex attributes we'll be working with. In this video going over the Triangle project, I've just been talking about position data. So the attribute of the vertices we're interested in is the positional data. The syntax here is a little goofy. We'll start out with the word layout. I just think of the word layout to mean that it's telling the vertex shader that we're about to specify how our incoming vertex attribute data is structured. It's basically an index. Next, in parentheses, we write location equals 0. This hard codes this specific variable to live in hardware attribute slot 0. We have this indexing because, like I said earlier, we have multiple attributes per vertex. In this case, we only care about the position unless you're doing the extra credit, in which case you'll want to be doing this for the color as well. Anyways, this is just going to be 0. If you had another attribute, you'd have another line just like this below, but the location would be 1, and so on. Now, you're going to use the word in to indicate that this is an input. And finally, you're going to give it a data type and a name, just like you'd expect. In our case, we're receiving 3D vertex position data, so the data type is called vec3, which means it's a 3D vector. In math, we distinguish between vectors and vertices, where vertices are the points that make up the shape, like a triangle. And vectors are essentially the arrows I mentioned in the last video. But since both of these are represented with 3 numbers, and we're going to do the same operations on them, in programming, we usually just use the vector data type. Anyways, now this vertex shader is set up to take in the positional data of our triangle vertices. Next, every shader has a main program. The syntax is simple. The main function just has a void main header, and the body of the function is inside those brackets. The only absolute requirement of the main function is that it must set a variable called GL_position, where the P is capitalized. GL position is the transformed location of the vertex. It's the output of the vertex shader that the rasterizer is going to deal with. The shader program needs to know this so it knows where it needs to render things on the screen. There's two important details here, both of which will pretty much not make any sense in this project. The first is that GL_position is a 4D vector. It's a vector with 4 components, x, y, z, and omega. For this project, just make omega 1, and we'll discuss it more when we talk about transformations in the future projects. One thing that's nice about GLSL is that one way we can construct a vec4 is by making the first argument a vec3 and the second argument the omega component. You can do this with vec2s and vec3s, it's a nice feature. The second odd thing here is that these coordinates must also be between -1 and 1, meaning that the coordinate space our screens use goes from -1 to 1. This is something called normalized device coordinates, and we'll also get into this more in the future projects when we talk about transformations. This is why our JavaScript array from earlier needs to have each component range from -1 to 1, so that we can just pass these coordinates straight through the vertex shader. And that's all we really have to do for this whole vertex shader. Now for the fragment shader. You still need to specify the version number at the top like you did for the vertex shader, but you need one more additional line of boilerplate. Precision high P float. This just tells the GPU to use high precision floats, which according to the GPU means 32 bits here. This is the standard, but you could also do something like medium P if you wanted. Now in the fragment shader, we're going to define an output variable to act as the output color. You put this above the main function and use the word out to specify that it's an output variable. WebGL expects an RGBA color, so this will be a vec4. The industry standard is to name this vector frag color. And inside the main function, you'll set this color to whatever you'd like. And that's it as far as creating the actual shaders. Next, we're going to quickly go over how the boilerplate on WebGL compiles, links, and uses these shaders, as well as how we connect our vertex attributes to the vertex shader. First, we need to call gl.createShader twice. Once for the vertex shader and once for the fragment shader. For the fragment shader, pass in the gl.vertexShader enum, and for the fragment shader, use gl.fragmentShader. Assign these outputs to variables. Now, for both shaders, call gl.shaderSource. The first argument is the shader object that you just created with gl.createShader. The second argument is the shader code as a string. Again, I'll show you how to easily turn these shaders into strings in the assignment description. Finally, for both the vertex and fragment shader, call gl.compileShader. Pass in the output returned from gl.createShader again. Once all these steps have been done for both shaders, call gl.createProgram with no arguments. Assign the output to a variable. This shader program refers to the total shader program that will contain the vertex and the fragment shader. Now, for both shaders, call gl.attachShader, with the first argument being the output returned from gl.createProgram, and the second argument being the output returned from gl.createShader. Finally, call gl.linkProgram, then gl.useProgram. That second call is telling the GPU these are the shaders that we want to be using going forward until we call gl.useProgram on some other shader program. For both of these calls, pass in the output returned from gl.createProgram. Now, I know that I didn't really go into those steps. That's because every time I make a graphics program, I just end up Googling all of this anyways. And I'm going to assume you know what compiling and linking a program is. If you don't, that's okay. It's not really important for this class. Now we're going to connect our WebGL buffers to these shaders, meaning we're going to get the vertex attribute data in the shaders to link up with the data in the vertex buffer we created. You're going to use a command called gl.vertexAttrib_pointer, which will automatically use the data in the buffer bound to array buffer. I'm not really sure how much space they thought they were saving on by using attrib instead of attribute, but I guess that's the decision they made. The first argument to this function is an unsigned integer, which acts as an index that corresponds to the attributes you defined in the vertex shader. The next argument is just an integer, and it specifies how many components there are per vertex attribute, meaning that if your attribute is something like a 2D vector, then it would be 2, and for a 3D vector, it'll be 3. Next is an enum for the type. WebGL uses its own enums here, but the options are gl.byte, short, unsigned byte, unsigned short, and float. I'm sure you can figure out which one to use for your position attribute. The next argument is a boolean which indicates if these values should be normalized or not. This only applies to data types like bytes and shorts, not floats. For our case, it'll be false. I've never actually seen this set to true before. Next up is an interesting argument called the stride. This is the number of bytes between each consecutive vertex. So if you have 3 float components per vertex attribute, you'd input 3 multiplied by float32array.bytes per element here. Or if you want to, you know that there are 4 bytes in a 32-bit float, so you can just use 12 here instead, or 3 times 4. The last argument to this function is the offset. This is where, in your data, byte-wise, the data for the attribute starts. For our vertex positions array, this is just 0. After you're calling this function, you'll need to call gl.enableVertexAttribArray and pass in the attribute index. This is a good time to talk about interleaving data, which will be important to you if you're doing the extra credit. It'll also be important in just about every other project. So you'll either want to learn this now or come back to it later. Let's say that you want to include both positions and colors as vertex attributes. One way you can do this is to put all your vertex positions at the beginning of the JavaScript array, and all the colors would go after those positions. And in this case, the offset you'd want to give to gl.vertexAttribPointer would be 9 times the size of the 32-bit floats, so 36 in total. And your stride would just remain 12. But we'd actually prefer if this data was interleaved. The reason for this is due to locality. If you've taken computer architecture, then this idea is familiar to you. But if you haven't, the idea is that our CPUs and GPUs have caches that it can access much faster than it can access memory. And when you access memory, the odds are that you'll want to be accessing that part of memory again, and parts of memory nearby very soon. So when we access data on RAM, our devices will copy this data and some data around it into the caches, since it'll likely be accessing it very soon, and we prefer to read from the cache rather than the memory. With this in mind, our vertex data is obviously grouped together. The location data and the color data belong to the same vertex. That information is going to be sent up together, so there's obviously some locality going on. So if we interleave this data, then this data that's grouped together ends up on the same cache, which is more efficient. If we do this, then the offset given to gl.vertexAttribPointer for the position will remain 0. But when we call gl.vertexAttribPointer, again for the color attribute, it'll be 12, since this color attribute starts after this first position is given in the array. And the stride for both calls will be the size, in bytes, of this entire vertex block. Alright, we're in the home stretch. So just a few more lines of code to get the triangle to show up, and maybe a few hours of debugging. Just like in the last project, go ahead and clear the screen. Now we're going to call a function called gl.viewPort, which essentially just sets up the camera dimensions. The first 2 arguments set the horizontal and vertical coordinates for the lower left corner of the camera. I've never seen these be any value other than 0. The last 2 arguments are the width and height. Go ahead and pass in your canvas width and height. Lastly, you're going to bind your index buffer. I then use a function called gl.drawElements. I'll come back to the first argument in a bit since it's an important topic. The second argument is the count. This just refers to how many of these indices you're using in your index buffer. So if you're drawing one triangle, you're going to pass 3, and if you're drawing 2, you'd pass 6. Although passing 6 would be a problem in our program since we have only one triangle to draw. So we get an error saying that our index buffer is too small. Next is the type of your indices. The options are gl.unsignedByte, unsigned short, and unsigned int. This just changes how many vertices you can draw. Technically, since you're only drawing 3, gl.unsignedByte would be more optimized, but our computers are so fast these days that there's very little reason not to just pass unsigned short or unsigned int. Finally, there's the offset into the index array. In some cases, you may want this to be something other than 0 for something called batching, but we won't go over it in this class. Okay, so back to the first argument. This specifies the kind of primitives to draw. Usually we're drawing triangles, like right now, in which case you're going to use gl.triangles. It does exactly what we've been talking about. It looks at each set of 3 vertices, treats them as though they're making up a triangle, and fills in that triangle. It does this to all the triangles just like you'd expect. Now we have line strip. This will draw straight lines to each vertex in the order that you give them. Next we have line loop, which is the same as line strip, except the first and last vertices are connected. Triangle strip is interesting. The first 3 vertices make up a triangle, and each vertex after that connects to the previous 2 vertices to create the next triangle. This requires the actual mesh objects to be carefully created to accommodate this, but it can be a great optimization when it's done, because you don't need to repeat vertices and you get to use far less indices. You also get great locality this way. Lastly, there's triangle fan, where each vertex given connects to the first vertex to sort of fan out. This can be another great optimization. In this class though, we're really just going to be using the triangles enum. And that's it for this video. Good luck on the project.